Welcome to another episode of Complete Developer Podcast, the podcast by coders for coders about all aspects of creating your best life as a developer.
I'm Will, the accomplished developer and aspiring software architect.
And I'm Beej, the journeyman developer sharing my journey in development.
This episode was sponsored by the PVS Studio team. It promotes static code analysis methodology in general and its PVS Studio tools in particular. Static code analyzers allow you to find bugs in source code at the development stage. This helps to reduce the price of fixing them.
PVS Studio performs code analysis and issues warnings on the fragments of code with a high probability of having bugs and potential vulnerabilities in them. The tool supports C, C++, C#, and Java, and it can work with Visual C++, GCC, Clang compilers, and some of those used for embedded systems. The analyzer works on Windows, Linux, and Mac OS. PVS Studio can both be used as a standalone tool and integrated with Visual Studio, IntelliJ IDEA, SonarQube, and so forth.
In the show notes, you can find links to the PVS Studio website and the article Technologies Used in the PVS Studio Code Analyzer for Finding Bugs and Potential Vulnerabilities.
1, 2, 5.
3, sir.
Right, 3. Whether you're throwing the holy hand grenade of Antioch or just ordering a list of students by grades, sorting can be difficult and confusing. While most higher level languages have some sorting algorithms built into them or in their standard libraries, they may not be the best option for what you're building. Understanding sorting will help you to use the most efficient method for your purposes. In this episode, we'll discuss sorting algorithms, how they are measured, and what to look for when selecting one. Then we'll look at several of the most popular basic algorithms. But before we get started, Will, what have you been fighting this week?
Well, I've got a new job, and this last 2 weeks I have worked 100% remote on a laptop provided by the company, hooked into all my other stuff here. And it's been great. Like, this is the best run dev shop I've ever worked for. Everything's on Azure. Like, I write code, I push it up, I do a pull request. It ends up going all the way to a server, automated for people to test. They have automated tests. And then when it's done, I merge it into master and push it up, and it's out the next day. And that is a stark contrast to what I was dealing with before, where I would make a change and it was 6 months before it was QA'd.
Oh, wow.
So it's been very interesting. I'm enjoying it a lot. It's a lot of Angular, .NET Core, Elasticsearch, Amazon stuff. There's all kinds of good stuff in there. So how about you?
Well, when this episode airs, we'll have more downloads than I owe in student loans.
In dollars.
In dollars, yeah. We hit 500,000 downloads this week. And I wish I were kidding, but y'all, med school was expensive. Speaking of school, it's coming to a close for the semester. Actually, by the time this episode is out, I'll have already finished. I don't have a final in this class. Well, I have an optional final, and it'll replace one test grade if I take it, but it's also comprehensive. And I already have a high B, kind of low A average in the class, and all I have to do is pass. So not really sure I'm going to do that. Just doesn't like...
You're not feeling it?
Yeah, the math doesn't add up to the time it would take for me to prep for the exam.
Well, and it is a math class, right? So for sure if the math adds up.
True. That's very true. Though I will say, for all the stuff I heard about discrete, I'm really enjoying the class. I think it's the professor. She's a comp sci professor, not a math professor. So she made it understandable for comp sci majors.
Yeah, and I think the other thing too is it may not, like, they'll use the word discrete and they mean more than one thing. Because ours was just like, it was high level math and it wasn't ever useful to me. Like, I've used lots of stuff from school, but I never used anything from that class. And what you're learning sounds actually useful.
Yeah, I have already applied several of the concepts. It's mostly high level concepts, but she applies them to computer science. And actually, the last few weeks, we've been learning about finite state machines, Turing machines, and formal language theory.
Yeah.
That's really cool. This weekend, we're going to be putting up Christmas decorations. Amanda's coming over. We're going to decorate my house. Been working on a few Christmas songs on the guitar, so I might play a little for her as well. Not that she hasn't already heard it, because we hang out all the time, and she hears me practice because I practice as often as I can. But speaking of practice, since our book this month is about art, you have to practice a lot of the arts that you do. So let's go ahead and jump into book club. So last week I started with a quote from the beginning of the book, and I'm going to reiterate that. This book is by Neil Gaiman, titled Art Matters Because Your Imagination Can Change the World. He says at the beginning of the book, the world always seems brighter when you've made something that wasn't there before. So the second section is titled Why Your Future Depends on Libraries, Reading, and Daydreaming. In it, he starts off talking about the importance of reading for pleasure. He even points out his bias as a writer that, he writes fiction. He wants people to read fiction. There's a little bias there. But then he focuses on encouraging children to read and states, I don't think there is such a thing as a bad book for children. While I understand the sentiment, I can think of a few shady books that might not be good for kids, maybe like 50 of them.
Or 50 Shades, as it were.
That was the joke I was implying.
Okay.
Gaiman goes on to talk about how reading fiction builds empathy and how a good librarian doesn't look down snobbishly at a person's choice of reading. He closes by talking about how the dead can still talk to us through literature. It's really odd, but when reading this book, I don't know if you guys have listened to any of Gaiman's speeches or his audiobooks where he narrates them, but I hear his voice in my head when reading this because it is very, very much him in what he's written here. So it's really cool. I'll have a link to it in the show notes. Who's talking to us this week?
Well, we got an iTunes review from Daniel Acolyte, I guess, or Acolyte, spelled like Acolyte with 2 T's. Huge career help. I absolutely love the format and the content of this podcast. The episode about burning up was a huge help in my career life. I found out that I was burning out continually months.
Daniel, thanks so much for the comment. We've both been at the point of burnout and beyond. Both Will and I learned a lot from that episode. Send us an email to waterbottle@completedeveloperpodcast.com with your contact information because we've got a Complete Developer water bottle just for you. Guys, if you'd like your very own Complete Developer water bottle, leave us a review on iTunes or comment on the website or any of our social media. We post all our episodes to Twitter, Facebook, LinkedIn. We're also on Instagram and Tumblr, though I don't think we've posted on Tumblr in a very long time. I will be sending out another batch of water bottles soon. If you haven't received yours yet, please email me at waterbottle and I'll check on it. It may be on its way. Yeah, let me know if you have sent me your information and not received one, and I'll get on that. You can join the conversation anytime via Slack by going to slack.completedevelopernetwork.com.
An algorithm is a finite set of instructions that are well defined. They can be implemented by a computer and typically solve a particular type of problem. They're used to explicitly define specifications for computer functionality. Found in mathematics as well, they're not limited to computer science. Basically, they are a set of rules that a computer or mathematician, sometimes there's little difference, uses to define a sequence of operations.
Sorting algorithms put elements of a list into a defined order. This could be numerical, alphabetical, or any type of ordering that you have. Sorting is also used in canonicalization of data. Now, that's a fun word to say if you've never tried to read it and say it at the same time. Algorithms are typically named with the word sort after them, unless the word sort is in the name. We'll get into that as we talk about the algorithms. Sorting has been researched since before computer science even existed. Adding computers to the mix speeds up the process, but it also adds a bit of complexity.
An algorithm must meet 2 criteria to be a sorting algorithm. First, the result cannot be in decreasing order. No element can be smaller than the previous element unless you're sorting in decreasing order, then it's flipped. The other is that the result must be a permutation of the input. is a reordering of what is input. New elements cannot be added.
Now, we've broken this episode into two parts. First, we're going to talk about the process of sorting and understanding sorting algorithms and what they do. Then we will look into several of the more common algorithms, discussing how each one works. So, first off, understanding sorting, we're going to talk about some of the properties of sorting algorithms. Sorting may be internal or external.
Internal sorts use local memory to store data while sorting. Data that cannot be placed in memory to be sorted must use external sorting. So typically, a merge sort or other sort that breaks the data into smaller chunks is used. An external storage device, such as a hard drive or flash drive, is then used to store the data while sorting.
Yeah, so in these larger big data things, they will take and break it down and then just sort the one piece and then store that, sort the next piece, store that, sort the next piece, store that. And then they'll come back and they'll bring two of these pieces and they're two pre sorted lists. So it's easier to merge those together.
Right.
And when we get into merge sort specifically, we will go into more detail on that.
That's also the way that we had to sort like way back in the day with, really hard memory constraints and those kind of things.
Yeah.
Like, big data used to not have to be that big. Like there was a time it was a floppy disk worth of data was a bunch.
Yeah. The definition of big has changed over the years.
Go to any Walmart and go to the chip aisle and you can tell.
I was just thinking about, I was at lunch the other day. I ordered a small drink and the lady pulled up. She's like, "Is this what you mean? This is our medium." And I'm like, "No, I want a small." And she pulled out, she's like, "Okay, well, we have the smaller size." I'm like, "All right, that'll work." But when I was growing up, that would have been a medium.
Yeah. It's like, I'm going to take this home and use it as a bucket. Thanks.
Yeah. So, in place algorithms are ones that do not use an extra data structure to hold temporary data. The change happens in the actual data structure itself. So, if you have an array or a list, it doesn't use a secondary array or list. It makes the change right there within that same array.
Right. By swapping elements.
A good thought example for this is kind of a code kata that it's not so much about the code, but about the way you think. And that is to swap the values. Integers are the easiest way to do this. It's like swap the values of two variables without using a third variable. So if you have a equals 10 and b equals 20, you want to swap those values. So to do that, you set a equal to a plus b, or 10 plus 20 equals 30. Then you set b equal to that a minus b. So 30 minus 20 equals 10. Now you have b equals 10. You go back to a and say, hey, set a to the current value of a minus the current value of b. So 30 minus 10 equals 20. And now you have b equals 10 and a equals 20.
Right. And so this is how you would do it in a really memory constrained environment, or
Yeah.
I would probably use XOR more than plus, but I mean, the point still stands because I'd be worried about overflows because I know I'd screw that up.
Yeah. I mean, it depends on what you're doing, but I did this in a math sense because it's sort of like basic addition you can kind of follow.
Right.
And look at the show notes for this because when you see it, it makes more sense than hearing it. But it's this idea of you're not using anything outside of what you already are starting with.
Right. So there are a few different ways to classify sorting algorithms. First off is based on their computational complexity. So you base this on worst, average, and best cases, because anytime that you're looking at sorts, you don't know what order the elements are in. So it could be like a best case where you don't have to move much stuff, or it could be worst case and you got to think about how that's going to play out.
Yeah. It's divided into the amount of time it takes to run an algorithm and the amount of space that process takes up in active memory. And we're going to talk a lot more about this a little bit later on in the episode. Next, sorting algorithms may be classified based on their general method of sorting. So, like insertion, exchange, selection, merging, and so forth.
Right. And bubble and quicksort would be exchange methods essentially there because you're copying stuff to either between locations or between locations in a third location that's a temp storage while you're
Yeah.
moving them around.
And then heap sort would be a selection sort. And if these are unfamiliar to you, we're going to talk about each one of them. And what we're saying now will make more sense by the end of the episode. So you can come back and listen to this portion. You're like, ah. I don't know how many of y'all listen to our episodes more than once, but I do. So,
Yeah,
oh, the life of an editor.
you don't
Oh,
anymore. We have a third party to help with that.
I still like to make sure everything
Yeah, I
sounds.
know because you're anal retentive. It's good though.
Yes. One of us needs to be.
Yeah, it's not going to be me, so it might as well be you.
Right, right. Algorithms may be recursive, non recursive, or have properties of both, such as a merge sort.
They may also be classified based on their adaptability. So if an algorithm takes into account the pre-sorted order of the input, it is considered adaptive. Algorithms that don't take into account the order of the input are not adaptive. So basically the idea here is if you have an incoming data stream that is sorted in some way or is predictable in some way, certain algorithms can adjust.
Yeah, and we're going to talk about that shortly. Finally, almost all sorting algorithms are serial, but they can be in parallel.
Right.
So, as Will was talking just a moment ago about adaptability, now we're going to talk about stability in sorting. An algorithm is stable if items of the same sort value in the input are in the same order in the output. So, what this basically means, before we get into the formal definition here, is that if you have multiple items, like you're sorting and you have multiple items with the same sort value, a stable sort algorithm will keep them in the same order that they're in when you input them to be sorted. Data being sorted can be represented as a tuple of values. The part of the datum used for sorting is called the key. The other part of the datum is irrelevant when it comes to sorting. So we're going to be talking about keys throughout this. When sorting a set of data, only part of the data may be used for the key. Stability is not a concern if all parts of the datum are used for the key. So if every little piece is the key, then it doesn't matter because they're all going to be unique. It's also not a concern if each of the datum used for sorting in the set is unique. So even if you only are using part of the datum as the key, if every piece is unique, then it doesn't matter. It's only if you have the same two keys that are the same.
So it's like if you're saying, okay, I'm sorting addresses and states, right? And the address isn't part of the key, then the sort order, is based on state. It may not remain in the same order.
If it's unstable.
Right.
If it's unstable, it'll remain in the same order that it's in there.
Right.
The formal definition is let A be an array and less than be a strict weak ordering on the elements of A. A sorting algorithm is stable if I less than J and A sub I is the equivalent of A sub J, which implies that pi sub I is less than pi sub J, where pi is the sorting permutation. Sorting moves A sub I to position pi sub I.
Right.
That is really heady and bleh. What that's basically stating is that elements retain their relative position after sorting. So let's say you have a data set of classrooms and sections of a class. You have 6 of these. So you have classroom 10 with section A, classroom 20 with section C, classroom 30 has section A, classroom 20 has B, classroom 10 has C, classroom 10 has B. This is your data set. To stably sort the set by room number, you would output from the list I just gave in that order. A stable sort of room numbers would be 10A, 10C, 10B, 20C, 30A. Because in the original set, 10C came before 10B and we're only sorting by the number.
Right.
And it maintained that order. To stably sort by the letter, if this makes more sense to you, you would do 10A, 30A, 20B, 10B, 20C, 10C. And that's because in the original order, like 20B came before 10B, 20C came before 10C.
Right. Yeah, it's a lot trickier in audio to do this than it is to explain it.
Look at the show notes for this one because when you see it, it'll make sense.
So, stability gets very important with nested sorting. Nested sorting occurs when you want to sort the same data set by multiple criteria. So, this creates a pseudo grouping of the data, with another group basically kind of under it.
Mhm.
You got to get that sort correct, in the first place, or the things underneath are not in the right order. If that makes sense.
For example, if you have a data set with student name, class, and grade, and you want to see grades in descending order per student, you would need to sort by both student and grades.
And you'd have to do it stably. Otherwise, one student's grades end up in the wrong place, or
Yeah,
it doesn't
they'll
look
be,
sorted. It depends on the algorithm, but it's going to come out weird.
yeah, if it's not a stable sorting algorithm. You're right. And the thing about nesting is it requires sort of a backward thinking on how you're sorting. What that means is that you have to start with the final criteria and then work backwards from the top level. If you've ever used Excel or other spreadsheets, this is how you'd group them. Going back to the student example, in order to see grades per student, where the students are in order, first you would need to sort by grades, and it'd just be like this jumbled mess of students and grades. And then you would sort by student because it would maintain that graded sort, and then it would kind of group that by student when you did that nested sort.
Right.
Whereas like the way you would think looking at it is look at student and then grade.
Right.
So it's like it's a backward thinking to get that sort the way you want it.
Yeah, because because this was one of the things, kind of thinking about how SQL does some of the things that really caused me a lot of heartburn early on. Is I would have looked at it as, okay, get all the students and then get the grades for that student and then sort those sets. And that's not
Yeah.
necessarily what's going to happen.
Right.
And so you'll get some weird behavior, especially if you are deriving keys or doing those kind of things, or,
Mhm.
summing up totals, for
Yeah.
instance. It gets weird very, very quickly. Any algorithm can be modified to be stable, any sorting algorithm. The key comparison can be artificially extended.
So like the comparison between two keys of equal value use the original input as their deciding factor. So you can extend what's in the key and like how that's compared. The thing about this is it requires adding more complexity to your sorting algorithm.
So would this be like you derive the key and you also have like another value in there to say, hey, here's where this thing was in, positionally, and you refer to the key first, and if those are the same, then you go to the other one?
Yes, that's exactly what it is. And another one is very similar to that, which is using a primary and a secondary key. In this, the secondary key may be the index or position in the list or array. It may be something else.
Right.
You could then use recursive or nested sorting to first compare primary, then secondary keys. Speaking of comparisons, the next thing we're going to talk about is comparisons in sorting.
Yeah. So comparison gets to be an also complex part of computer science. Looking at stuff, we'll look at two numbers and go, this one's bigger than the other one. Right. But there's a lot of times in comp sci that you will get things that you don't expect. This happened in Python 2. There was if you did not implement like the comparison operator on a type, it would look at the memory locations and compare the memory addresses or something along those lines. And so you would get just, bat crap crazy sorting that like made no sense to anybody. And so you'll run into a lot of this kind of stuff. So comparison is something that you have to get down and get explicit in the algorithm. Otherwise, it's going to do something else.
So, what they do is a comparison algorithm compares keys at each step in the algorithm. And this is used to decide in what order to place the keys being compared. Generally, they're easier to implement than non comparison sorts. They read the list of keys through a single abstract comparison. This is usually a less than or equal to operation, but it could also be a three-way less than or equal to or greater than operation. The comparison operation must form a total pre-order over the data. What this means is it involves using the transitive property from algebra. So basically, what that is if A is related to B by some property and B is related to C by that same property, then A is related to C. Or more mathematical, if A is greater than B and B is greater than C, then A is greater than C. So if 10 is greater than 5 and 5 is greater than 1, then by the transitive property of algebra, I do declare that 10 is greater than 1.
Yeah. And by the property of null, you don't get to declare. That's why I said it's kind of important to know exactly what your comparison is.
Yeah. The other thing is comparison algorithms are connex relationships. And this does not mean that your ex went to prison.
That's I was wondering, I'm like, oh, is it story time?
A connex relationship is a homogeneous relationship where all the parts relate in some way. For instance, A and B. A is less than or equal to B, or B is less than or equal to A. This is for every possible pair of A and B in the set. So either one is greater than the other or they equal each other, is what it's saying.
Now, it is possible for two keys to equal each other. Mathematically, A less than or equal to B and B less than or equal to A. That's also true when A equals B.
Yeah. In this case, either key may be first in a sorted output. However, as we mentioned earlier, in a stable sort, the input order determines which comes first. Usually it's the chicken.
Oh, man.
Hey, this is some heady stuff. I had to throw in some weirdness somewhere.
Yeah, I think you've had some weirdness thrown in just in general.
Oh.
On average, comparison sorts cannot be faster than O of n times log n.
Yeah, and we'll get more into that momentarily. This is averaging the best possible and the worst possible runtimes. A set that is already sorted or has some unique factor is going to run faster. There's only one version of the list that is sorted, but there are n factorial times n factorial possible versions of a list.
Right, of n items.
Yes. Good catch there.
Yeah.
Chances are very low that the list will be input already sorted.
At least by the key that you want.
Right.
Now, integer or counting sorts do not make comparisons. With all these, the keys are integers. So an integer sort determines how many keys are less than the given key. So, for instance, if there are 14 elements less than the key, then it will be placed at position 15 because you know where it goes.
Yeah. This places each element immediately into the correct slot without having to rearrange the list on each permutation. Integer sorts are not limited to an average time of O of n times log of n.
Right. I would think you'd be able to almost get constant time because you're looping through, and for each of them, you're just going, hey, put it there where it goes until you have a collision, and then everything goes south. So never mind, scratch that part. But it could get up to constant. Could be as good as that.
Yeah, it's best case. It's big O of omega. It's big omega. That's what I meant to say. And we'll talk about that now. Speaking of complexity and efficiency, it's important to know how well an algorithm will run when choosing which one to use, right?
Well, it depends. Are you a contractor and you're getting paid to fix it?
So all sorting algorithms output a sorted list. That's what they do.
Hopefully.
However, we're running with the presumption that they actually work at this point. The way they go about sorting affects the efficiency of the algorithm. Some work better with large data sets, but not well with smaller ones, whereas others may be more efficient with smaller data, but get hung up with the larger data sets.
Right. Or they may not properly prioritize things like moving stuff in memory because there may be some aspects that more expensive and you don't want to do it. For instance, if you're writing to disk.
Yeah, there's a give and take here.
Yeah.
Knowing the worst case is very important for systems that need guaranteed performance. This will tell you how your system will work under a real time load. Also, it can be used to mitigate DDoS and other attacks that try to overwhelm a system.
The running time of an algorithm is how many operations it has to do before it completes. And this is also assuming the operations are the same size, which is what I was talking about before. But
Yeah.
to keep it simple, that's why we do this. Each operation takes a set amount of time. So this is a description of how long it takes the algorithm to complete.
So big notation is used to describe algorithms' time efficiency. Big O, which we've had an episode about, and you should go back and listen to it if you haven't already, describes the worst case running time, meaning the algorithm will never be any slower than its big O notation.
This is like a programmer estimate in Agile. It's like, this is this many story points. This is the worst case because I don't want to get fired.
Yeah. But this is like when an algorithm says this is its big O, that means it will not ever run slower than this.
Whereas big omega describes the best case running times, meaning the algorithm will never be faster than that time. So this is a sales estimate.
I like that. That's good. Yeah. And big theta describes the case when big O and big omega are the same.
Which
so
is
this
an
is
estimate
reality.
from an Agile planning book.
There also exists an average case running time, meaning that on average, the algorithm will not be slower than that time. And in some of these, we'll talk about how the big O and the average are the same. That doesn't mean that it's a big theta, because you may have a best case that's not that way, but the best case is, it's a pre-sorted algorithm or something. Or it's
Right.
already got partial sorting. Like we said it earlier, the worst case for comparison algorithms is big O of n times log to the n. That is the slowest that it will run. It's also the average.
Space complexity is another thing that comes into this, and that's how much space in memory or external storage is needed to run the algorithm. So, for instance, if you're writing code that is flying to Mars, right, they have less memory available, right? They're not going to just cram the thing with terabytes of storage.
Yeah.
Well, they might now, but like in 1977, they wouldn't.
In-place algorithms have the smallest space requirement. That's constant, O to 1, because they don't need any extra memory. They use exactly what is given to them. Space complexity uses the same big O notation, or omega, big theta, that we just discussed. For example, if an algorithm needs a list of size n, and in the process of sorting creates a second list of size n, then the algorithm needs n squared space in memory.
That seems odd that it's n squared instead of 2n.
It's n squared for Wikipedia.
And I think the reason for that is because of all the shuffling back and forth of, it's not that you're just copying and going, hey, this one goes here, this one goes here. It's because you're continually moving stuff around and you're going to have to reallocate constantly. That's why that's that way. Because I just was thinking somebody was listening, they're probably going, why isn't that 2n? That's why.
Why? Yeah. So right along with what Will's talking about, the last thing we're going to talk about in understanding sorting is problems with sorting data.
Yeah.
The way that sorting algorithms use or overuse memory can become a problem. This can be very large data sets.
Yeah, and very quickly, right? I mean, we just talked about it squaring the amount of space.
When you know you're going to be sorting large sets of data, you can choose your algorithm to suit that.
Right. Bubble sort all the way.
Oh, yeah, baby. Bubble
sort and then go to lunch. That's how you do it. It's professionals.
At the bar.
Yeah. In Florida.
Till next week. Yeah.
Where they don't know your name or your phone number.
However, if you do not expect large data sets and get them, you may run out of space in memory.
Right.
When running out of memory, the algorithm may use slower hard disk or external storage.
Or it may just catch on fire. So you hope.
It depends sort of on what platform you're running and what their backup for running out of memory is.
Right. Like on Windows, it would page to disk and it would, reallocate the heap and.
And this context switching becomes an issue if you have to swap to and from disk. I mean, it slows the time down, but it also eats up more memory while it's transitioning. When you're working with complex records, such as relational databases, Creating an index and sorting by the index reduces the amount of memory that you need to sort.
Because you're sorting pointers
Yeah.
to the original record. I mean, that's, the idea is it's a pre-cached
Yeah.
sort position. As previously discussed, various algorithms have different time costs to run them. And there's generally a trade off between memory and time when you're choosing an algorithm. So if we ever come to a time when we have enough memory, it's not going to take any time to sort anything at all because it's all going to be pre sorted.
Yeah. With real time systems, you want to run only the most necessary processes and algorithms. It is best practice to assume the worst case scenario on time for an algorithm. Not doing this could cause latency and other timing issues when you do get unexpected data to sort. Now, I got a cool quote from Dennis Waitley. It says, expect the best, plan for the worst, and prepare to be surprised.
Because you probably didn't even think about the worst.
Most people don't. We've talked about that in several episodes, especially in like our testing episodes on don't just test the happy path. When you're picking an algorithm, don't just pick it based on the happy path.
Right.
To reduce live sorting time, pre-sort or batch longer sorting processes.
Right. And you'll see this a lot with reporting databases where they'll go
Yeah.
ahead and they'll have all these indexes in place so that they're not having to sort at runtime. In fact, that's usually pretty common practice with your relational databases anyway, is to do that because it hurts if you don't.
Yeah. Sorting speeds up searching, but it's not necessary for searching. And we're not really talking about searching in this episode. We'll have another one at some point in the future about searching algorithms. But I did want to bring this up because when you're searching a large data set, it is faster if it's sorted.
Right.
However, sorting takes time. So you're going to sacrifice in either the search or the sort. So if you can pre-sort your data in a batch overnight so that it's available and ready to be searched when it needs to be, you can speed this process up. But if all that's needed is an unfiltered search result, then searching alone may be faster.
Yeah. Determining when to sort and when not to sort can also be kind of confusing. There's a lot of factors involved in that process, and we're going to have an episode on the topic. Also, bear in mind when all this stuff we're saying it with the presumption that it is a single thread,
Yeah.
and that you don't have 500 people trying to do the same thing, because that gets interesting too. Or mutating data, like we're assuming a static chunk of data, not mutated, and you're sorting. Once you get into relational databases, it gets a lot worse, a lot quicker.
Yeah, that's true. We didn't even go into that because that is its own episode. So, we're going to close out this episode talking about some common sorting algorithms. This is not an exhaustive list, and these are mostly just basic sorting algorithms. You've probably heard of quite a few of these. We start with simple sorting algorithms. These algorithms are the easiest to implement and maintain. Typically, they work best on small data sets due to the low overhead. However, efficiency drops quickly as the data set gets larger.
An insertion sort is an efficient algorithm for small and mostly sorted lists. Typically, it's used in combination with another sorting algorithm.
Insertion sorts by taking an element from the list and inserting it in the correct position. This takes up extra memory because it requires a new list of sorted elements. The old and new list can take up the same space, but that requires moving elements over by one when you do it.
Right. So it's got to be a really small list for this to be efficient.
Right.
If you're playing that game. Doesn't change the relative order, so it is stable. And because it builds a new list one item at a time, it's O of n squared and requires constant memory. In other words, it's O of 1.
Yeah. The sort performs at big O k times n, where k is the greatest distance between two elements. And because it's possible for them to be at opposite ends of the list, the worst case is n. So it's O of n times n.
Right.
Selection sort compares elements without using another list or memory space. It is best with smaller data sets, though it is not as efficient as insertion sort.
Yeah, it has a time complexity of O of n squared. And what selection sort does is it divides the input into two parts. The first is a list of sorted elements, and this is built at the front of the full list. If using arrays, it will then start at index 0. The rest of the list is the unsorted elements. So it's just kind of cramming it on to the beginning to get this sort worked out.
Yeah. As the algorithm runs, the list of unsorted elements dwindles as the list of sorted grows. its advantage comes when there is limited memory for other sorts. So now we're going to talk about what you're more likely to see. These are your practical or efficient sorting algorithms. Efficiency of sorting comes from a reduced time complexity.
Yeah, and almost all of these algorithms will have an average time complexity of O to the n times log of n. That means they're all comparison sorts. And in most cases, the big theta will also be O of n times log n.
The cost comes in space complexity. This can range from O to the n at best and O to the n squared at worst. The space issues are often resolved by combining these with other sorts. And these algorithms are likely to be used in several languages and standard libraries. So the first one is one we've already mentioned, and that is merge sort. This relies on the ease of merging previously sorted lists.
Yeah, this is used in several different programming languages. In Perl, it's the standard sort routine. In Python and Java, it's part of the standard routine. It's also used in combination with insertion in the complex timsort algorithm.
Yeah, so merge sort and insertion sort have made a resurgence because of this timsort algorithm that's relatively new. And we're not going to talk about complex sorting algorithms, but these are ones that combine the basic sorting algorithms.
So I got a fairly serious question. Did the whole skit with Monty Python and the holy hand grenade at the beginning of this episode, did that come from, you may call me Tim?
I have no idea. I don't know anything about timsort. I honestly didn't even look it up because we're not talking about complex
No, I just
sorts.
was thinking, like, when I saw that, I was like, is this why he put that at the beginning? Because it just seems like something you would do.
I wish.
Okay.
If that would be really cool. But no, I did not. But I would not be surprised if it did. It probably comes after someone's name.
Yeah. Probably some guy named Tim or Timothy.
Yeah. It works by breaking the data into smaller lists. This starts by comparing every two elements and making lists for each of those comparison. It then combines or merges the lists of two elements into lists of four elements. This continues until the last two lists are merged. It works well with large data sets having big O time complexity of O to the n times log of n. However, it sacrifices in the memory because it has to create so many sublists.
Yeah, these things take up a ton of extra space. The space complexity is going to be O of n.
Yeah. Quicksort is another sort algorithm that works through use of multi-branched recursion.
This is called a divide and conquer algorithm. It recursively breaks down the problem into smaller problems. It works backward from the merge sort, which starts with the smallest comparison and then builds up.
It uses a partition operation that partitions an array on a pivot. So all elements smaller than the pivot are moved in front of it, and all elements greater than the pivot are moved behind it.
Yeah, the tricky part is choosing the pivot element then, right? Because you need to know some kind of statistical breakdown of what's in that thing so that you're not pivoting most of them around to the wrong side.
Mm-hmm. Constantly choosing a pivot on either end of the sort causes the time complexity to drift upward toward O of n squared. However, this is a rare occurrence, and the typical performance is closer to that average of O of n times log of n.
Because it doesn't have to create separate lists for moving the elements around, it's another in-place algorithm with a space complexity of O of log n.
Heap sort is an efficient version of the selection sort. Like selection, it breaks the data down into two parts, sorted and unsorted. Time efficiency improves by using a heap. This is a special type of binary tree structure. The root node of the tree is the extreme element, or the largest or smallest, depending on the direction of the sort. The node is removed and placed at the end of the list, and then the next node becomes the root.
This speeds up the process of finding the next element, making the big theta O of n times log n. Now, a shell sort is another one, and it's a more efficient version of the insertion sort. Its name comes from its inventor, Donald Shell, which I always thought that it was like the shell game thing. So this makes a whole lot more sense that it's some dude's name. I feel better,
Yeah. It moves the out of order element more than one position at a time. This first sorts elements farther away from each other. The gap between elements progressively shrinks, causing the algorithm to get faster as it runs because it's kind of pre sorting the list as it goes down to, whereas insertion just compares side by side elements. This goes and it starts at a gap and it progressively compares all the elements at that gap, and then it gets smaller and compares all the elements at that gap. So it kind of pre sorts it until it gets down to that small one, and then it just quickly runs through it.
Right. And that's why you can't really calculate the time complexity very well.
Yeah, it runs more efficiently on mostly sorted data sets, just like insertion sort. And like it is an in place algorithm and doesn't require any extra memory.
So we also need to talk a little bit about distribution sorts. In distributed sorts, the data is distributed into intermediate structures before being combined. So this is used usually for handling very large amounts of data that has to be sorted.
Yeah, data too large to be stored in memory is able to be broken down and stored externally while other pieces of the data are being sorted. I kind of alluded to this earlier in the episode. This can happen on a single processor, or it can be broken down and processes on several different processors.
Counting sort is used when you know the input is within a particular set. We'll call it S. It's extremely fast, especially the smaller the set is.
Yeah. It works by creating an array of size S, the amount of elements in set S. It then counts the occurrences of a particular member of the set and places them in their own bin. The inputs are then counted by incrementing the associated bin. The counting array that is created is then looped to put all the inputs in order.
And this is going to have a time complexity of O of the size of the set plus N.
Yes. So if you're looking at the show notes, I've got the two pipes around S. That's not the absolute value of S. That is set theory, which means the size of the set,
right,
like the length of the array, basically. The memory required is just the size of the set, so O to the amount of elements in S.
A bucket sort is another divide and conquer algorithm. It builds on counting sort to allow for larger data sets. Bucket sort will take an array and divide it into a finite amount of buckets or bins. Each one is sorted individually. This can be using a different algorithm or by recursion. When using recursion, it's pretty similar to the merge sort. The exception is that merge sort doesn't have a set number of buckets or sublists. Also, bucket sort doesn't necessarily break them down into two element comparisons.
It works best when the data is evenly distributed, and the efficiency is determined not by the bucket algorithm, but by the algorithm used to sort each bucket.
Right. And I could imagine that they would even potentially switch that out as they're going along, depending on, potentially what's in there.
Bubbles! It's time to talk about bubble sort. Bubble sort and its variants are simple to learn, but extremely inefficient. They are mostly seen in textbooks, tutorials, and my mind.
And whiteboard interviews.
Whiteboard interviews, yes, I have done some bubble sorts in whiteboard interviews, yeah. While they are used for studying sorting, they may actually be used in research around sorting. They're rarely used in the wild due to their inefficiency. Honestly, if you see this in practice, you've probably found a recent graduate, maybe.
Yeah. Or somebody that just got it working once and didn't touch it again and hadn't heard them yet. There's a surprising number of those people out there. Bubble sort is one of the simplest sorting algorithms. It's most commonly taught because it's extremely intuitive to understand how you're sorting this stuff. It's the way you would probably sort physical objects by hand.
Yeah. What it does is it starts by comparing the first two elements in the list. If it needs, it swaps those elements. Then it moves to the next two elements in the list, compares them, and swaps if needed. Once it's reached the end of the list, it goes back to the beginning and does it again. And it keeps going through this, doing these two one at a time comparisons until it goes through the entire list and makes zero comparisons.
Right. So, like we said, efficiency problems. It's like the way that somebody would sort a card catalog. I know a lot of our listeners are probably not old enough to remember those. If somebody with like almost no memory, no working memory, tried to sort a card catalog, that's how they would do it.
Yeah. Bubble sort is plagued by rabbits and turtles.
Aren't we all?
The distance and direction each element must move affects the performance of the algorithm. So, rabbits are elements moving to the back of the list because they move faster. Because they, like, if you have, let's say you have a list of integers ranging in size from 1 to 10, and at the very beginning of the list is 10,
Yeah, it's a rabbit.
10 is a rabbit. It's going to move all the way back. Turtles, on the other hand, are elements at the back of the list that need to move forward. If you have 1 at the very end of that list, it can only move 1 time per loop through the list because the list is unidirectional. It's only going one way.
Right. So this basically works out where you have a big theta of O of n squared, which is pretty horrendous as far as performance.
Yes. And it's not used often with large data sets. Even
But if it ever was, it's still running. So they got that going for them. It's most efficient with semi-sorted data when the lower efficiency is not a problem, aka CS101 class.
Yeah. So Will's favorite sort, the cocktail shaker sort, is a variant of the bubble sort. It is a stable comparison sorting algorithm that attempts to deal with the turtles in bubble sort.
Unlike bubble sort, which is unidirectional, cocktail sorts in both directions. It functions basically the same as the bubble sort. Instead of restarting at the beginning of the list, it moves backward through the list, comparing the elements and making the opposite comparison to put them in order.
So basically, going back to the example of the list of integers 1 through 10, if 1 is at the bottom of the list, 1 becomes a rabbit moving up the list in cocktail sort. Instead of being a turtle once every loop, it's, when it's going back up, it's winning every comparison back to the top of the list.
Yeah, even though it works in both directions, it's only slightly more efficient than bubble sort. The time complexity has a big O of n squared and a big omega of O of n, but it averages at O of n squared.
Since it is in place, the big theta space complexity is O of 1. Now, the final one we're going to talk about, the comb sort. This is the one dreaded by all balding people.
That just makes the list smaller.
Comb sort is another simple algorithm based on bubble sort. Its purpose is to eliminate turtles from bubble sort, just like the cocktail shaker. And it starts off by swapping elements at a certain distance from one another. Sort of like the teeth in a comb are a certain distance from one another.
Okay.
This is opposed to only swapping elements side by side in bubble sort. If you think back a few minutes to one of our previous sorts where the shell sort worked at a gap that progressively got smaller, it's kind of similar to that, but solving a different problem. Like the shell sort, the distance between elements gets smaller until it's basically doing a bubble sort. And like I was saying, comb sort is to bubble sort as shell sort is to insertion sort. So, y'all, this is designed to help you better understand what goes into a sorting algorithm. The ones that we discussed are basic algorithms. I know this episode has been rather heady, and we've tried to make as many goofy jokes as we can to lighten it up along the way. Hopefully, most of them will make it into the episode. Most languages and libraries use complex algorithms that combine several of these basic sorts. You can use this information when you're deciding how to sort data sets in your code. Try writing some of these in your language of choice to get a feel for how they are designed. That pretty much wraps us up. Before we close everything out, Will, what do you have for us this week for Tricks of the Trade?
Well, a sorting thing, actually, but it's a little different. When you get a job, you need to figure out how your boss is sorting the employees. In other words, how are they evaluating, is this employee better than this other employee? And get that figured out explicitly or by watching how the boss reacts to things. For instance, this is sort of like the concept of a key in a sort. If you know how the key is derived, you know what the sort order actually is. And because you're a person, you can manipulate your key, as it were. In other words, the criteria that is used to sort you. You need to look at your boss and actually try to figure out what they're looking for. I worked at a company where we initially thought that we were judged by our productivity. And that was not the case. We were judged by how well we came up with estimates and how close those estimates were to reality. Not based off of how much we could get done, but off of the number of surprises we created, with the lower numbers being better.
Yeah.
And not knowing that is extremely painful because it can really hurt you as far as your career prospects. So, this kind of fits in with the same thing, is understand how you're evaluated. And if you don't know, you need to stop what you're doing right now and go figure that out. And don't necessarily ask your boss, but observe how they react to people acting differently and derive what that is. Because a lot of times they won't tell you. This is really important for your career, is to figure that stuff out, because it'll help you a lot. So I'm just suggesting you do that. That's all I got.
Stand by for Titanfall.
If you have a question or comment, please email us at neckbeards@completedeveloperpodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed through Creative Commons.
The intro music for IoTs is Hillbilly Hip Hop by Jason Belcher. For references, show notes, and to sign up for weekly emails with extra tips and insights, be sure to check out the website at CompleteDeveloperPodcast.com. You can also follow us on Twitter at CompleteDevPod and like our page on Facebook to keep up with news about the show. Catch us each week as we broadcast live, talking about what's going on in the tech world and answering listener questions.
Learn more about all of our shows and groups by going to CompleteDeveloperNetwork.com, where you'll find links to Junior Developer Toolbox, Developer Launchpad, and our other communities. Thanks for listening. See you next time.